A human genome once took years and $95 million to read. Now the bottleneck is no longer measurement, but how fast labs can test ideas. At 5:43 on a Thursday morning, a man sits in a hospital corridor in his socks while his partner sleeps behind a curtain after another biopsy. More than 5.14 million academic articles were published annually as of 2022. Yet no clinical team can manually search, compare, and test that flood fast enough for every patient waiting on a treatment clock. That is why 68% of researchers now say AI is helping accelerate their work. At places like in silico medicine, the system is not one model, it is a stack. Machine learning to rank targets, large-scale compute to search chemical space, and automated lab workflows to test what survives the first pass. The real question is not whether science feels faster. It is whether AI, data, computation, and robotics have turned discovery itself into a closed loop that can compress years into months without flooding medicine with faster mistakes. Science is usually slow for a simple reason. Each result arrives too late. A researcher observes something, proposes a hypothesis, designs an experiment, waits for instruments, analyzes the output, then decides what to test next. That loop is serial. 3 things changed. First, measurement got cheap. Sequencing fell from more than $95 million in 2001 to about $525 by 2022, with some estimates now near $200. Biology became machine-readable at scale, faster than Moore's law. Second, compute exploded. In headline AI experiments, compute rose by more than 300,000 times between 2012 and 2018, doubling roughly every 3.4 months. Third, models learned to compress patterns inside huge datasets into ranked predictions. But here is where the old workflow breaks. Once reality is turned into data, AI can search possibility spaces no lab team can inspect manually. In molecular simulation, new AI models can run more than 10,000 times faster than conventional methods. That does not mean the chemistry is solved. It means weak candidates can be rejected earlier, before expensive wet lab work begins. Then, robotics takes over the physical loop. A self-driving lab does not just move pipettes. It selects the next experiment, runs it, measures the result, updates the model, and redesigns the next trial automatically. Some of these systems cut the number of experiments needed to reach a conclusion by 30-fold. In drug discovery, that compression is already visible. In silico medicine has moved candidates into preclinical development in about 18 months. Traditional early discovery often takes 4 to 6 years. But the most counterintuitive shift is not in medicine. It is in search itself. Microsoft and PNNL reported AI systems identifying 500,000 stable materials in days. Another system narrowed 32 million possible inorganic materials to 18 battery candidates in just 80 hours. If 32 million materials becoming 18 in 80 hours sounds impossible, stay with CivilizationX. The constraint behind that number comes next. That is the new regime. Science is no longer limited mainly by too few ideas. It is limited by too many possible ideas to test. The bottleneck moved from imagination to search, then from search to verification. And that is where the system starts to fight back. Publication output surged 21% from 2015 to 2019. By 2022, annual output passed 5.14 million articles. More than 53% of published papers are never cited. Peer review is overloaded. If AI trains on noisy literature, it can accelerate noise, bias, and irreproducibility at machine speed. The same math shows up in screening. Imagine a model searching 1 million molecules where only 1% are truly useful. At 99% specificity and 99% sensitivity, it finds about 9,900 real hits, but also flags about 9,900 false ones. Precision is only 50%. Speed alone can still waste half the lab. So yes, science is moving faster in measurable ways. Sequencing is vastly cheaper. Simulations can be 10,000 times faster. Self-driving labs can cut experiments 30-fold. Drug programs can reach preclinical stages in 18 months instead of 4 to 6 years. But predictions alone do not create knowledge. The candidate still has to be synthesized, measured, reproduced, and shown to matter in the real world. Over the next 5 to 15 years, the strongest systems will not be chatbots for scientists. They will be traceable discovery platforms, standardized metadata, remote instruments, autonomous planning, and hard validation at every step. That is the logic behind materials acceleration platforms already being built. If they work, the next milestone is routine closed-loop design of drugs, batteries, and climate materials inside one auditable system. Back in that hospital corridor, what changes first is not fate, it is timeline. A tumor can be sequenced in days, compounds screened in hours, and a patient's biology made legible to medicine faster than even a few years ago. The unresolved engineering problem is harder. How can autonomous scientific systems be engineered so every AI-generated hypothesis, experiment, and result stays fully traceable and reproducible, from raw data to clinical decision? Would you trust a machine-run lab to guide treatment if every step was auditable but not fully understandable? The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem. Stay with CivilizationX.